Hello everyone, my name is Xiaoyun Fu. Today we're going to learn minimum spanning trees and the Prim's algorithm that can find minimum spanning trees in graphs. To succeed in today's class, I expect you to know the following concepts ahead of time. First, you need to know the big O notation for runtime analysis. And for data structures, you need to know the basic ones like arrays, hash tables, heaps, and the runtime of their common operations. For discrete math, you need to know basic functions, and for algorithms, you need to know how loops work. And finally, for graphs, you need to know the basic representation of graphs like adjacency list, adjacency matrix, and edge list. Back to today's topic, let's start with the real-life problem. Suppose a flood washed away all the roads between a bunch of cities. I hope you guys don't experience such terrible floods in your area. Now an emergency response team is called to restore the connections between those cities. Well, constructing roads takes different amounts of time, and in such emergency situations, we don't expect them to restore all the previous roads, but just enough roads to make the cities connected as soon as possible. So in this situation, which roads should they reconstruct first? Here's the process we usually use to solve real-life problems. We first abstract and model them in math problems. Then we compare this math problem with the similar problems we have learned before and see if we can modify that solution to solve this problem. So in an algorithm class, one of your jobs is to learn the main categories of problems and corresponding strategies and build up a solution reservoir for you to use in the future. So back to this situation, we can model this problem as a graph problem, and we're going to learn a greedy strategy to solve it. Now let's model it. The cities can be represented by vertices in the graph, and the roads between cities are the edges between vertices. And finally, the amount of time taken to construct each road can be expressed by a weight function that maps from an edge to a real number. For example, the weight of the edge AB is 4. This may represent constructing the roads between A and B takes 4 hours. Alright, so overall we can model the input to us as a weighted, connected, undirected graph. And our goal is to find an acyclic subset of edges that connects all the vertices and whose total weight is minimized. By total weight, we mean the sum of the weights of all edges in this subset. You may wonder why we want the subset of edges to be acyclic. Intuitively speaking, we don't want to waste time or money or resources on connecting vertices that are already connected. In this flood example, the priority is to connect all the cities as soon as possible. Creating cycles takes extra time that doesn't broaden the connections. Alright, so since this subset is acyclic and it connects all the vertices, it must form a tree, which we call a spanning tree, because it spans the graph. It contains all the vertices in the graph. And since its total weight is minimized, it is a minimum spanning tree, MST. Now, how can we find such minimum spanning trees in graphs? I'll let this question sip in your mind for a while, and I'll get back to it later. For now, I want to introduce you to greedy strategies in general. By greedy, we mean at each step, among all possible choices, we make the choice that is the best at the moment. Believe it or not, you already use greedy strategies a lot in your life. For example, after high school, many students have a bunch of choices. To name a few, go to college, find a job, or even become homeless. I guess those who showed up in college most likely valued all the possibilities at that stage and thought going to college was the best option for them. Whether it's true or not, we don't know. Now let's see another example. Let's play a game. I have $1, a dime, and a penny. Which one do you want to take home with you? Well, I guess anyone who's not too bad with math would take the dollar coin. That's right, because that's the best you can get for now. That's what we call greedy. Always make the best choice at the moment. So you take that dollar. Alright, now let's play the second round of the game. You guys don't even know there's a second round? That's right, it's life. It's full of surprises. So in the second round, based on your previous choice, you automatically get an extra coin. You get a penny, a dollar, and a dime, respectively. Now I will give you 1 second to figure out how much you get in total. Alright, so those who chose the dollar coin, have you figured out? Being greedy at the beginning doesn't assure you the best deal. I'm sorry I tricked you, but unfortunately, this is the reality for greedy strategies in general. Although you make the best choice every time, that sequence of best choices doesn't guarantee a globally optimal solution. Why? Because when we make those greedy choices, we lack a global view. Alright, so the next time when you need to make a life decision and you ruled out a bunch of decisions, but you are just left with the 2 choices, and you are torn between those 2 choices, remember this lesson. There's no need to struggle, because even if you pick the best one at the moment, it doesn't guarantee an optimal life. That being said, we still use greedy strategies a lot. Why? Because they are intuitive and efficient. And sometimes we are forced to use greedy strategies because we just don't have the global view. When you guys played the game, you didn't know all the rules. When we make life decisions, we don't know what the future is. Another reason we use greedy strategies is that sometimes they find the optimal solution, and in cases they don't, they usually give a good enough solution. Remember that greedy guy who chose the dollar coin at the beginning? They got a pretty good deal overall. Alright, that's greedy strategies in general. Back to this minimum spending tree problem, we're going to learn a specific greedy strategy called Prim's algorithm. In the future, we can prove Prim's algorithm actually finds the optimal solution, but for now, let's just learn how it works with this example. The strategy goes like this. We'll start from an arbitrary vertex, let's say vertex A, as the current minimum spanning tree. Next, we expand the minimum spanning tree 1 vertex at a time until we span the graph. Now, here comes a question for you. Which vertex should we expand to each time? The hint is, it is a greedy strategy, so you need to make the best choice every time. But what is called a best choice? Now you have 30 seconds to think about that. Ready? Go. Alright, time's up. I hope you have come up with some ideas. Let's compare your idea with my idea. So it is a greedy strategy. Being greedy, we always expand to the vertex with the minimum cost to include. Here's what we mean by minimum cost. In this situation, the current minimum spanning tree is A. If we want to expand it to one more vertex, we have two choices, B or G. To expand to vertex B means we add the corresponding edge AB to the current minimum spanning tree. And since this edge AB has a weight of 4, the cost to include B is 4 through this edge AB. Now, what is the cost to include G? It is 5 through the edge AG. And which one do we prefer, B or G? Being greedy, we prefer B with the lower cost. Why? Because our goal is to build up a tree with the minimum weight. So we prefer lower cost. Alright, so the current minimum spanning tree contains the edge AB. It doesn't span the graph, so we need to keep going. In the next round, what are the candidates to expand to? You may say C and G. That's right, but in principle, D, E, F are also the candidates because they are all outside the current minimum spanning tree. So among these 5 candidates, let's figure out their cost one by one. Vertex G could be included through the edge AG with a cost of 5 or through the edge BG with a cost of 6. So what's its cost? 5 or 6? It's 5 because we prefer lower cost. Alright, so its cost is 5, but that doesn't mean we add the edge AG to the current minimum spanning tree now because we still need to compare it with other candidates and see who wins. Another candidate C could be included through the edge BC with a cost of 5. Now, vertex D cannot be reached immediately from the current minimum spanning tree now. So it has a cost of infinity. The same is true for E and F. So when you guys said that the candidates are C and G, that's right. Because if you think about it, among all the candidates, only those candidates who have immediate connections with the current minimum spanning tree have a chance to win because they have finite costs. Alright, so in this situation, both C and G have the same minimum cost. That's not a problem. That just means this graph has multiple minimum spanning trees. So for now, let's break the tie by alphabetic order. So we expand to C. Now the current minimum spanning tree has AB and BC. After class, you can try the other choice of the tie and see if the tree you get there has the same weight as the tree we get here. After expanding to vertex C, the cost of its neighbors are affected. The neighbor B is already in the minimum spanning tree, so we don't need to worry about that. But the neighbor D, who was unreachable, is now reachable through the edge CD with a cost of 6. So we need to update its cost from infinity to 6. The same is true for F and E. So F's cost is updated from infinity to 2, and E's cost is updated from infinity to 9. Because we have found better ways to possibly include these neighbors to the current minimum spanning tree. That's the reason for the update. So we finished the current round, we expanded to vertex C, and we updated the cost of its neighbors if needed. In the next round, we just repeat this procedure. Among all the unselected vertices, which are our candidates, we expand to the one with the minimum cost to include. Which is the one we expand to this time? It's F with the cost of 2. And again, with this new membership of F in the current minimum spanning tree, the cost of its neighbors are affected. Vertex C is not affected because it's already in the minimum spanning tree, but vertex D, who was reachable through the edge CD with the cost of 6, is now also reachable through the edge FD with a cost of 2. And since this new cost is lower, we need to update its cost from 6 to 2. The same is true for the neighbor G. G has a cost of 5. And now we could also include G through the edge FG with a cost of 1. 1 is lower, so we prefer the lower cost, so we update G's cost from 5 to 1. But for vertex E, E has a cost of 9 now, and with this new membership of F in the current minimum spanning tree, we can also reach E through the edge FE with a cost of 10. But since this new cost is higher than its current cost, we prefer the lower cost, so its cost stayed as the lower 9. Alright, so this finishes this round. We expanded to vertex F and we updated the cost of its neighbors if needed. Remember, we don't always update the cost of its neighbors. We only check if there's a better way to possibly include that neighbor. If there is, we update the costs. Okay, let's go for another round. We just repeat the same procedure. Among all the unselected vertices D, E, G, we expand to the vertex with the minimum cost, which is G in this case. And again, we need to update the neighbors if needed. Among all the neighbors of G, A, B, F are already in the current minimum spanning tree, so we only need to check the neighbor D. D has a cost of 2 now. And with this new membership of G in the current minimum spanning tree, we can also reach D through this new edge, GD. But since the new cost is higher than the current cost, we keep the lower one, so there's no update for D. So we finished this expansion. We expanded to G and updated the cost of its neighbors. I bet you guys are an expert on this procedure by now, but I have a challenge for you in the next round. In the next round, among all the unselected vertices D and E, we expand to the vertex with the minimum cost to include, which is D in this case. Well, here comes your next test. When we are about to add a new vertex to the current minimum spanning tree, how do we know through which edge to add it? Not just for D, but in general, every time we add the new vertex, how do we know through which edge to add that new vertex to the current minimum spanning tree? Now you have 30 seconds to think about that. Let's go. All right, time's up. Let's check your ideas. Think about how a vertex gets its cost in the first place. It is the edge weight of the edge that connects it to the current minimum spanning tree. And it keeps updating if there are new ways, better, lower cost ways to connect it to the current minimum spanning tree. So every time we update a vertex cost, we can also remember who gives it this new cost. Let's call it the parent. For example, for vertex D, the first time its cost is updated from infinity to 6, it is through the edge CD, so C was its parent. And later on, when its cost is updated from 6 to 2, it is through the edge FD. So we update D's parent to F at that point. Later on, it also had a chance to update its cost through the edge GD, but it didn't because that cost was higher. So its parent and cost stayed as the same as 2 and f. Now with this parent information, when we are about to add a d to the current minimum spanning tree, we know it is through the edge of d and d's parent at that time. So that's why we expand to d through the edge fd. So actually, after the expansion to the new vertex, we need to update both the cost and the parent of the neighbors if needed. In this case, since these neighbors are already in the minimum spanning tree, so no updates for them. Okay, let's go for the last round. Among all the unselected vertices, which is E only, we expand to the vertex with the minimum cost to include, which is E, so we just need to expand to E. But through which edge? You know, E got its cost of 9 through the edge CE. Later on, it had a chance to update its cost from FE with the cost of 10, but it didn't because that cost is higher than 9. So E's parent and cost stayed as C and 9. So now when we are about to add E to the minimum spanning tree, it is through E and its parent, which is C. So we add CE to the current minimum spanning tree. And then we update the parents and the cost of the neighbors. And since both neighbors are already in the minimum spanning tree, no updates for them. Okay, I know I said last round, but if we try to go for yet another round, we will find there are no unselected vertices. That means the current minimum spanning tree has included all the vertices. That's great. That means the algorithm terminates. Now let's review the whole process. Initially, the current minimum spanning tree is empty, and each vertex has a cost of infinity and a parent of null, because none of them is reachable from the current minimum spanning tree yet. Next, we pick an arbitrary vertex and set its cost to 0. This serves as a starting point of the current minimum spanning tree. Then we expand the current minimum spanning tree one vertex at a time through a loop. In each iteration of the loop, we expand the current minimum spanning tree to the vertex with the minimum cost to include. And we update the cost and parents of its neighbors if needed. When the loop terminates, we have a complete minimum spanning tree. Now comes your third test in today's class. Which data structures can we use to achieve such a greedy strategy? The hints are we need to keep track of all the unselected vertices, and among them, we need to pick the one with the minimum cost. And we need to regularly update the cost and parents of its neighbors. Among all the data structures you have learned, which data structures can support such operations efficiently? Now you have 30 seconds to think about that. Let's go. All right, time's up. So the answer is we need a priority queue to store all the unselected vertices and extract from it the element with highest priority, which is minimum cost in this case. Well, priority queues have many implementations. You can use arrays, linked list, hash tables, or many others. But we prefer a heap structure in this case, more specifically a main heap. Why? Because in a min heap, to extract the element with the minimum cost takes order log n time. And to update the element's value in the min heap takes order log n time each time. We will discover the runtime details later. So with the priority queue, the first step is to initialize the priority queue with the cost of the vertices as the key. The queue stores all the unselected vertices. While the queue is not empty, we extract from it the element with minimum cost. And we add the corresponding edge to the minimum spanning tree. After that, we update the cost and parents of its neighbors if needed. Here we only need to update the neighbors who are unselected, meaning they are outside the current minimum spanning tree. They are still in the heap. So to do the updates, we check for each neighbor v of u if this neighbor is still in the queue and its current cost is higher than the new cost through this edge uv, then that means we have found a better way to possibly include this neighbor v to the current minimum spanning tree, which is through the edge uv. So in this case, we update v's cost to the lower new cost, the edge weight of uv, and v's parent to u, because it's through u that v could be added to the current minimum spanning tree. And since this neighbor v is still in the queue, once we update its cost to a smaller value, this may break the priority queue property, so we need to fix the queue. And now we are ready for the next round. So this is the whole Prim's algorithm. Basically, we have 3 stages: initialization, expansion, and update. Well, you probably haven't noticed that in the input, the weight function maps an edge to a real number. That means the Prim's algorithm actually works for both positive and negative weights. In the future, when we prove the correctness, you will see why. Now let's analyze the runtime of Prim's algorithm. I want to go into excruciating detail because I want you to understand the runtime of such algorithm structures once for all. So now let's first figure out how the inputs are stored, because it affects how we process them in the algorithm. The input graph G can be stored in an adjacency list, adjacency matrix, or an edge list. Now let's just assume our input graph is stored in an adjacency list, which is the most common way to store graphs. You can think of this adjacency list as an array of lists. The array is indexed by the vertices, and in each slot, it stores a linked list of neighbors of their vertex. For example, vertex A has 2 neighbors, B and G. So storing B and G as a linked list in slot A represents 2 edges, AB and AG. In an adjacency list, every edge is directed. The way we represent undirected edges is by storing 2 directed edges. For example, to store the undirected edge AB, we actually store 2 directed edges, AB and BA, in the adjacency list. So overall, this adjacency list stores 2 E edges in total. So that's for the input graph. How the weight function is stored will be discussed later. Now let's go into the algorithm to analyze them line by line. Let's first analyze the initialization stage. We need to figure out a way to store the cost and parent for each vertex. For the parent, it can be stored in a parent array, which is indexed by the vertices. So that takes order v time. When we say order v, it's actually order the size of v, but we're just being lazy. For the costs, since the priority queue uses the cost as the key, we can actually store the cost directly in the priority queue. And for the priority queue, we use a binary min heap with an array implementation because we know there will be at most v elements in the heap. That's why we can use an array instead of using a linked structure for the min heap. To initialize the min heap, usually we fill in all the values in the array and then heapify from bottom up to fix the violations of the min heap. But here's the special case. You see, each vertex has a cost of infinity except for the vertex R. So we only need to put vertex R and its cost at the root of the min heap. And the other keys can be anywhere. So it takes order v as well. So overall, this initialization stage takes order v time. Next comes the while loop. Initially, the priority queue contains all the v vertices. In each iteration of the while loop, we extract one vertex from it. So how many iterations can the while loop go? V vertices in total. One by one, we get it out. So there are v iterations for the while loop. And now, how much time does this extract min operation takes each time? Here's how we extract the minimum element from a min heap. We take the root value and replace it with the last element in the heap. This new value may be too big for the root, so we may need to swap it with its children, and in worst case, all the way down to the bottom. So it takes order the height of the heap many swaps, in worst case. So that's why its runtime is order log v for this extract min, because after that extraction, we still need to fix the min heap. Alright, once we get this new vertex, we need to add the corresponding edge to the current minimum spanning tree, which can be done in constant time. So overall, this expansion step takes order log v time in each iteration. And since there are v iterations, overall, the runtime for the expansion stage in total is order v log v time. Alright, that's the expansion stage. Now let's analyze the upstate stage. The upstate stage is done through a for loop. So imagine the whole process. The priority queue contains all the vertices at the very beginning. In each iteration, we extract one vertex from it, and we explore its neighbors through this for loop. For example, when the new vertex is A, the for loop checks the neighbors B and G through the edges AB and AG respectively. Later on, when the new vertex is B, the for loop checks the neighbors A, C, G through the edges BA, BC, and BG respectively. So overall, the while loop goes through each vertex exactly once. And the for loop goes through each edge instant on that vertex for exactly once. And since the adjacency list stores 2e edges in total, the for loop goes for 2e iterations in total. If you still don't understand this, we can visualize this process. When the new vertex is A, the for loop checks two neighbors, B and G, through the edge AB and AG. Later on, when the new vertex is B, the for loop checks the neighbors A, C, G through the edge BA, BC, BG respectively. So this edge AB has been visited twice. Once when A is the new vertex and once when B is the new vertex. Will this edge be ever visited again in the future? No, because the only way to reach this edge is through A or through B. And once A and B are pulled out of the queue, there's no way to reach this edge anymore. So this edge is visited exactly twice. And the same is true for all the other edges. Each edge is visited exactly twice. That's why we have 2e iterations for the for loop. Now let's go into the for loop body. The if statement checks two conditions. It first checks whether the neighbor v is still in the queue or not. Remember, the queue is a heap with an array implementation. So how much time does it take to check whether a vertex is in this array or not? Well, if you don't have any extra information, then you virtually need to search the whole array. And that takes order v time. It's too expensive. Now, how can we reduce this search time? You can use some extra space to store some extra information if needed. So what extra information do you want to store? You may think we can have a Boolean array to store a Boolean value for each vertex, whether they are in the heap or not in the heap. You are right. A Boolean array is sufficient for this membership check. But if we are going to store an extra array for these vertices, we better as well store more specific information. For example, the specific heap position of that vertex, because that heap position is useful information for other checks later on. So we're going to store the heap position of each vertex in the heap using an extra heap position array. When a vertex is pulled out of the heap, we mark that heap position value in this array as a negative number to indicate they are gone. And when a vertex moves around in the heap, we update its heap position value in this array accordingly. So with the help of this extra heap position array, this membership check can be done in constant time. That's great. You know, sometimes using a bit of extra space can save us a lot of time. So when you develop algorithms, you always need to consider the trade-off between time and space. Now let's check the second condition, which is a comparison. Now, how can we get the cost of a vertex? Remember, this neighbor v is still in the queue, and the queue stores all the costs. So if we know its position in the queue, we can go directly get the cost there. Remember, we have this heap position array, so if we know its position, we follow that lead to go to the heap and get its cost there, which can be done in constant time. That's why we want to store the heap position instead of just a Boolean array. Alright, that's great. Now comes the edge weight of UV. How can we get this edge weight? The edge weight is given to us as an input, so it depends on how the weights are stored. For example, if the weights are stored in an adjacency list like this, then to get the weight of a specific edge, we potentially need to go through the whole neighbor list. And if the graph is dense, the neighbor list can be as long as v, so it's kind of order v in worst case, which is not preferred. On the other hand, if the weights are stored in an edge array or can be computed using a formula with constant time, then we can get the edge weight in constant time. So again, a trade-off between time and space. Okay, so this if statement takes constant time for the check. Inside the if block, to update the cost of v takes constant time. Why? Again, because we know the position of v in the heap. So we follow that lead and just go directly to the heap position of v and update its cost there. Update the parent of this neighbor v can be done in constant time as well, because the parent array is indexed by the vertices. So that's easy. Now we need to fix the queue. When the new vertex is U and the neighbor is V, which is B in this case, for example, when we update this neighbor's cost to a smaller value, this may break the heap property. So to fix it, we may need to swap it with the parent because the new cost may be too small and that violates the heap property. So we need to swap that. In worst case, we may need to keep swapping until it reaches the root. So in worst case, order height of the heap many swaps. And that's why its runtime is order log v. So overall, the if statement takes order log v time for the whole block. And since there are 2e iterations for this if block, the update stage takes order e log v time in total. Alright, so overall, the initialization stage takes order v time, expansion takes order v log v time, update takes order e log v time. And usually e is larger than v, so the overall runtime is order e log v. If you want to be precise, you can also write order e plus v times log v time. Alright, that's the runtime for Prim's algorithm. A brief summary. We have defined the minimum spanning trees today, and we talked about the properties of greedy strategies in general, and we learned a specific greedy strategy called Prim's algorithm to find the minimum spanning trees in graphs. We also talked about data structures we can use to help Prim's algorithm achieve its best runtime. However, the algorithm structure I just talked about works best when the input graph is stored in an adjacency list. If the graph is dense, it's usually stored in an adjacency matrix. So if we just follow that algorithm structure, then the runtime would be order v squared log v if the graph is in an adjacency matrix. That's not good. So we need to think about ways to reduce the runtime to order v squared. So that's for you to think about. We still use the same structure as Prim's algorithm. We start from an arbitrary vertex and we expand to the vertex with minimum cost each iteration. And in each iteration after the expansion, we update the neighbors, cost and parent if needed. Remember, we only update the cost and parents of those unselected neighbors. A hint for you is, okay, we need to drop the log v for the runtime and think about where does this log v come from, and maybe we need to drop that structure. All right, so that's for an alternative implementation of the Prim's algorithm when the input graph is in adjacency matrix. To finish the minimum spanning tree topic, we also need to prove the correctness of Prim's algorithm, and we can also cover some practice problems like maximum spanning tree problem, where the goal is to find a spanning tree with maximum weight, or the minimum spanning forest problem when the input graph is not a connected graph. And lastly, we need to learn another greedy strategy for the minimum spanning tree problem, which is called Kruskal's algorithm, and do a comparison between Kruskal's and Prim's algorithm. That will be the whole minimum spanning tree topic.